Bueno, muchas gracias a Christoph por esta interesante charla y invitamos a pasar a Ari Friedlander. Ari Friedlander es investigador científico en el Laboratorio Marino de la Universidad de Duke, Carolina del Norte, en Estados Unidos, y va a hacer su presentación sobre uso de hábitat a pequeña escala.
Thank you very much, Barbara, and thank you everybody for coming and for everybody who's presented so far. I was kind of frantically writing down as many notes as possible because just about every slide had something of interest to me, as well as trying to think about ways to link what folks have been talking about at this very broad scale and ecosystem level to what I'd like to talk to you about, which is looking at whale behavior more at the individual level and talk about the fine scale habitat use of cetaceans. And one of the things that came to mind was what Lisa had mentioned earlier, looking at how whale behavior and other predator behaviors in the Antarctic interact. And the thing that I take home from that, having done some of that work, was that I was really jealous because a lot of the penguin data that came from there was individual based and had something about the consumption of the rate of the animals and more biological information than just simply the presence of whales. And what I'd like to talk to you guys a little bit now, and hopefully that will help to add some complexity and some knowledge to these models, is we can now get a better estimate of what these whales are doing underwater at the very individual level, not only on the dive but in particular behaviors. And this information hopefully will give us a better estimate of what a whale can do and does do, that we can then extrapolate out to some of these larger ecosystem questions, not just in the Southern Ocean but in some of the ecosystems around the Southern Ocean that might be closer to shore or that might involve humpback whales in other parts of the world. Again, thank you to the Southern Ocean Research Partnership. This has been, in my mind, the most exciting and invigorating way to bring scientists together who do different kinds of work and have different kinds of questions, but to be able to merge these kinds of things is phenomenal. And the folks who have made this, the support of this possible is exciting. What I'd like to do is just briefly introduce foraging behavior, very basic concepts, and then talk about humpback whales specifically. And I'm only going to talk about humpback whales, but a lot of what we're talking about obviously applies to other cetacean species. Talk about advances in how we study these whales, and Christoph did a great job of introducing this, and I'll talk specifically about one piece of technology that we use, as well as how we visualize underwater behaviors of these animals. And I'm a very visual person, and when I see those big equations that were put up on the board, I get a little nauseous myself. So I need to be visual when I'm trying to understand what these animals are doing. And then at the end, I just want to link what we're showing in terms of whale foraging to prey ecosystems, as well as conservation. There are certainly applications of this information beyond studying ecosystems around the Antarctic to other areas as well. So very simply, to put us into lunch mode, foraging is an interesting topic, and foraging predator strategies depend on a couple of things. First off, you have your physical constraints, which this puffin clearly doesn't understand its own constraints by how big your mouth is. Cetaceans are interesting in that respect. What type of teeth or baleen you have, how you actually capture your prey, how deep can you dive, how long can you spend on an individual dive, and how do you actually capture your prey. And humpback whales, as you'll see, are a fine example of that because of their morphology that allows them to do interesting things. But on the flip side, prey also behaves in a way to try and preserve itself, and pufferfish is clearly doing that here, and I'm sure a lot of krill wish that they had some mechanism to avoid predation risk as well. But how prey affect whale behavior is something that's very interesting too, and something that, unless we measure it directly, we don't understand how the decisions that whales make might be affected by changes in their prey. I went to Africa a few years ago for the marine mammal meetings and immediately became frustrated on a safari because everything was very obvious. You saw the leopard, you saw the impala, you saw it run, jump on it, and then start eating it. And there was no guesswork involved. We didn't have to come up with new technologies and new analytical techniques. You could literally just watch everything happen, and it gave me a little better perspective of the things that we need to learn and understand about whales when they're underwater, and the things that you need to be able to measure. You need to measure the predator as well as the prey, and to some level the environment that all this interaction is happening in. This is typically, I'd say this is a good day for a whale biologist. There's actually something at the surface here. It's flat, there's a bird, and you can see something is at least making bubbles here. And this is a pretty good day for some of us. But it does beg the question of everything that's happening below is just as relevant as the previous slide. We just don't have an actual way of seeing it. Some people are able to get up in the air and see these kinds of things. And again, humpback whales, I think in the cetacean world, offer sort of one end of the spectrum for the ability to see these kinds of behaviors, but hopefully with application to other types of animals. Most folks have seen sort of these XY dive plots before, and the very basic information you can get from something like a time depth recorder. And there are many ways to make this information more functional ecologically. And one of the ways that I'm going to talk about how we do this is to add in distribution and abundance of prey. So in the upper right-hand column, or the figure up on the right, is a small boat that has scientific echo sounders. These are basic fish finders. I'll talk a little bit more about them, but they give us at least a relative measure of the amount of prey that's in the water column, how it's behaving, whether it's in patches or layers or individual targets. And then we can begin to do things like overlay where we see whales diving to and simply address, are the animals feeding on higher densities of prey? Are they going deeper than they have to find the most dense prey? And get a better understanding of what the environment is around where these whales are making these dives. So, echo sounders. Not being an acoustician myself, I have to keep things very simple. Basically, when we put sound into the environment, it scatters and it bounces back off of individual targets, and the amount of sound that comes back is going to be a function of the species, the size, and the orientation of the individuals in the water column that the sound is bouncing off of. And we can use this approach, very simply, to measure the density and biomass of prey. And one thing that's very important to understand is this can be a very relative measure, but if you do have the opportunity to capture individual preys and understand what the strength of the response or what a target strength is of an individual krill or an individual herring, you can become quantitative and not just get a relative measure of abundance, but an absolute measure of the biomass or the density of the prey that these animals are encountering. And that's just sort of that's my math on the bottom there, is the school backscatter divided by the target strength equals the number of prey, and you can get an idea about how much prey is available to animals that way. So this is an animation that some folks may have seen at other conferences, but what it shows is at the sort of scale of an individual whale, how we're able to map prey around tagged animals, and hopefully this will start. If not, it's not a big deal. Oh, meeting not found. That's great. Okay. Anyway, we'll move on from there. What I measured, you can use echo sounders to map the distribution and abundance of prey. You can see in this figure, here's a couple of different ways that we see that. You can have individual targets, you see in the upper right-hand part of the water column, or you can have aggregations or patches of prey. And there's probably some function towards how whales feed that makes a vertically oriented patch of prey versus a horizontal patch of prey very different. And I'll talk about that in a little bit with respect to humpback whales. We're all very familiar with them, very wide distribution of animals, individually identified. But the thing that makes them unique and that I'm going to talk about are the large flukes and flippers that allow these animals to be a lot more maneuverable. I think of them as being much more slow than maybe a fin whale and a blue whale, but they use the adaptations that they have in their morphology to take advantage of prey and a lot of resources in very different ways. And the tool that I'm going to talk about is the D-tag that Christoph mentioned before. It's a small, lightweight tag that's non-invasive, that's applied with suction cups. It collects data for up to 24 hours, and it uses this combination of sensors to collect information on the depth, as well as the pitch, the roll, and the heading of the animal, which gets sampled at very fast rates, as well as the hydrophone. And I'll show you sort of the unique application of using the hydrophones in combinations with these sensors to understand the behavior of these animals. I'm sure this is going to tell me median not found too. No. Christoph and most folks have said, they've mentioned this harsh Antarctic environment that we work in, and I beg to differ a little bit. This is in the Antarctic in May, and this is a humpback whale where we're deploying the tag on, and it's not slow motion. It's quite big, and you can see the extreme reaction from this animal to the tagging event. You see the Zodiac kind of hits it, and then the whale wakes up. It's embarrassing. It's got ice on its head, and it had no idea what was going on. But you'll see my buddy Dave here. Luckily, you can't hear the audio because it gets kind of embarrassing. But that whale basically went back to. There's Dave. Say hi to Dave. When these tags are on these animals, they're, at least for an animal the size of a humpback whale, they clearly don't affect the behavior of the animals. They go back to doing what they were doing. That animal went back to being comatose about 5 minutes later. But they provide us a good opportunity to deploy tags on these animals. And like I said, if you're wise enough, you can go to the Antarctic and to places in the time of year where you're not dealing with massive seas and big swells. And that's might be my greatest accomplishment, is finding some calm water in the Antarctic. Sorry, it might be a little difficult to see this. This is again sort of the old school time depth plot that we used to see in a lot of papers, that just simply shows the depth of the animal over time. And what we can do, aside from just seeing how deep these animals dive, is get some idea about what the behavior of these animals is. This is what it looks like when the animal's sleeping at the surface, this basically flat line up at the top here. What's interesting about this is we can start to understand the movement patterns and behaviors of whale once we know what the prey are doing. So in the Antarctic, you only have about this much daylight in the winter when we put the tags on, but the whales essentially sleep all day, and they make some exploratory dives very deep in the water column. And then right around sunset, which is about 2 o'clock in the afternoon at the end of May, the animals start diving and feeding deep, and I'll show you how we can tell that these are feeding dives. But what you do notice is that this animal has a very dramatic change in the depth that it's feeding at as night occurs, and then as night ends and comes into the next day, you see that the distribution of where these feeding dives occurs is very different. And we know that animals are obviously going where their prey are, so there's something in the behavior of the prey here that are affecting the whales. And in this case, this whale makes it very easy for us to understand that as prey move vertically in the water column at night, they're affected by that, and they move their feeding to overlay with where that occurs. So one of the ways that we're able to pull out apart some of these more fine-scale behaviors is to use a program called TrackPlot that a guy named Colin Ware developed about 7 or 8 years ago, and that we've continued to develop and add some flexibility into it. And it's a free program, and he's a great guy and is extremely excited about working with people who have tag data and trying to get the program to pull out either sensors or measurements that people are interested in. And what this essentially allows us to do is to make a track, and I'll show you in a second a better one, but basically a track that shows the orientation of the whale underwater. The red and the blue carrots that you see here are actually fluke strokes that can be pulled out of the accelerometer readings. So you can see when the animal is fluking on an ascent versus when it's gliding down on a descent. And you also get an idea about the orientation of the whale, and then since there is space involved, you can see how much area the whales are covering. So this is sort of the massive spaghetti plot over time if you look at what a whale is doing over a long period of time. But you can see kind of in the background you see an animal that's basically going down, and you see some of this sort of surface behavior going down, feeding, up, down, and then you see some very interesting patterns that occur if you start to pull out the plot sort of one bit at a time. If you look at an animal that's underwater, so the surface would be up here, and this whale is down at the depth here. I think these bars equal about 10 meters. Here's an animal that was at the surface. It dove down here, and then you can see it's sort of doing these little checkmark patterns along its dive. Hopefully folks in the back can see this, but what we're able to do is take the accelerometer readings from this animal when it's moving either nearly vertical up or down, and we can calibrate that with the flow noise from the tag. So think about driving in your car. If you roll the window down and you're at a stop sign, there's not a lot of noise. And as you start to accelerate, if you put your head out the window, it'd be very loud. And so we can generate an estimate of the speed of the whale by how much sound is on the tag. And we use that then to try and infer when feeding behaviors occur. So in humpback whales, when they feed, they accelerate very quickly, open their mouths, which is essentially a big parachute, and they stop very quickly. Their acceleration stops very rapidly as they open their mouth around prey. So we can look for signals in the prey, in the sensors that indicate when the animals are feeding. So on the right-hand side here, you see an animal that's kicking pretty heavily right at the bottom of this dive, and that's essentially what these green lines show here is fluke strokes, and the animal's accelerating very quickly. And then as it opens its mouth right around here, right after that fluking, you can see a dramatic decrease in the acceleration. So it's opened up its mouth underwater, and we can say this pattern in all of the dive profiles represents where these animals are taking a bite underwater. So then you can automate these sorts of things and have undergraduates and graduate students go through the hours and hours of tag data and pull out all of the times where you see this type of feeding event occur. And that gives you an idea of how many times the animals feed on an individual dive, and then when you start relating that to the prey, you get an idea about what they need to feed and what the conditions are like when these animals begin to feed. So it's a very powerful tool to learn what the animals are doing underwater, and then to also just visually see how their feeding behavior occurs relative to their environment. What we can then do is sort of step out slightly in scale and look at a more broad spatial scale over sort of the course of a tag deployment, maybe say 8 or 10 hours. And when we put sort of a metric of how much prey is in the water column versus where the animals are feeding, we get a much better idea about what these whales are doing. So on this plot, what you see is the blue areas are places where there's very little prey, and then the red and yellow areas are where you have high densities of prey. And every event or surfacing or dive is indicated by an X on this plot. And the white ones are areas where the whales were not feeding, and the black ones are areas where the whales actively fed. So you can see that the whales are pretty good at finding where the prey are in their environment, and then traveling between places where there's very little prey, up to a spot where there might be a small dense patch, and then you move around. They don't find everything, but when they do find areas of high quality prey, because we know what they are doing underwater and we're measuring the prey, we can make that direct connection. So bubble net feeding is sort of another case that humpback whales do, and we were interested in seeing what the conditions were that make humpback whales bubble net feed. And what we found that's interesting, and I mentioned this before, is that humpback whales are much more likely to feed in a bubble net when the prey are oriented vertically in the water column as opposed to when they're sort of horizontal in the water column. And this is, I call this the Pringle hypothesis. Folks are aware, Pringles, the potato chips that come in this nice canister. And if you had Pringles that were stacked up in a column, you could just take the can and stick it on top and you're going to get all of the prey. If you spread the Pringles out on a table and just kind of do that, sorry, that's a little violent. If you kind of do that, you're only going to get 1 or 2 Pringles. So it's a very functional way for these whales to maximize the amount of prey that they're taking. So you take the whole can rather than making a bubble net around something like that. And in track plot, we have the ability to animate these and see actually how the kinematics or the orientation of the animals actually change when they're doing these kinds of behaviors. So this is a whale that does something that's called kick feeding, where it goes at the surface. You saw the animal kind of do a little seesaw thing, and what it's doing is it's coming up to the surface, kicking with its tail, and then going down underneath the prey and making a bubble loop, and then coming up in the middle of them. And the yellow areas on this track indicate where the animal is rolling on its side. So it may either be using that to help bank around and make a very tight turn, or it may be even looking at the prey as it's doing this behavior. But animating these tracks in 3 or 4 dimensions allows you to see the orientation of a whale in a much better way than if you just had that simple XY dive profile. The thing we've learned about humpback whales that's really interesting is that you have individuals that have different techniques. So some of them do single loops like this, some of them do double loops, some of them probably can get pretty dizzy doing 3 or 4 loops, and then there are some animals that probably don't get it quite as well. But the fact here is that you have individuals that are doing something that looks basically the same, but there's variation among the individuals in how they do this, and just having the ability to measure this amount of flexibility in their behavior shows us how much individual variation there is. And I'll just end with one more sort of interesting facet of humpback whales, is that they also feed on the bottom. They don't just take advantage of prey in the water column. They're able to actually go to the bottom and take advantage of prey. And there's some folks in Cape Cod, and maybe even around here, who notice this very active scarring or shearing on one side of their rostrum. And we put tags on humpback whales and thought we might get this, and this is exactly what we found, is that at some times of day the whales will go to the bottom, roll on their sides, and much like gray whales, kind of stick their heads in the bottom, roll over, stick their head in the bottom, and keep doing that over and over and over. What's interesting about the way that the humpback whales are doing this is, if you look at sort of the larger picture, you see that these animals are doing them in very simple, straight lines over and over, almost at the same heading. So they're taking advantage of a prey resource both in the water column at the surface as well as around the bottom. And here's just, you can see that these animals do them over, over lines and over periods of time, and they're pretty well able to figure out where their prey are. I won't spend too much time on this, but what we find, and this is not the case in the Antarctic, but in Cape Cod and probably in other places, the prey that they're doing these behaviors around change their behavior between day and night. So animals bubble net feed during the day when their prey are distributed in the water column, and then when the prey go into the bottom or the sediment at night, they change their foraging behavior to take advantage of that. So humpback whales show, like I said, sort of this extreme case of being able to change their foraging behavior based on how their prey is behaving. And using these multi-sensor tags and these very fine-scale tags along with measurements of the prey is what allows us to gain these inferences. So just to kind of summarize, these tags have allowed us to understand that humpback whales have unique adaptations that allow them to do these foraging behaviors. And by combining prey data, tag data, and this visualization technology, we have a much better understanding of how these whales forage, as well as other whales would be able to forage. And we're starting to understand the relationships between whales and their environment. And these can be used, as folks have talked about in some of the other talks, to better understand whales as ecosystem models or as parts of ecosystems to protect and conserve them. And that's it. Thank you.